triangle ABC is inscribed in circle omega. The interior angle bisector of angle A intersects side BC at and omega at D and L other than A, respectively. Let M be the midpoint of side BC. The circumcircle of triangle ADM intersects side AB and AC at Q and P. And we let N be the midpoint of segment PQ, and H is the foot of the altitude from L to line ND. And we want to prove that ML is tangent to the circumcircle of HMN. So we want to prove that the red things are tangent to each other. So how can we get started on this problem? The only thing that seems to be standing out of the open is this point H, because we want to now decipher everything that's going on in this diagram. So let's go ahead and draw in LH and see if we can use advantage of this right angle here. Well, so we know that LHD is 90 degrees, but we also know that LMD is 90 degrees since LM is perpendicular to BC. This is because L is the midpoint of the arc and M is the midpoint of BC, so it's the perpendicular bisector. So this angle is also 90 degrees, which means that DHLM is cyclic. So now what? So let's go ahead and erase these now that we know that this holds. And given this, we want to somehow relate this condition here to the cyclic quadrilateral DHLM. And using what we know about angle chasing for tangent circles, it suffices to show that angle LMH is equal to directed angle MNH. But directed angle LMH is equal to directed angle LDH because they inscribe the same arc in the circumcircle of DHLM. So this is directed angle LDH, which is directed angle MNH. We want to show that these are equal. So we want to show that this angle here is equal to this angle here. But this only happens when AD is parallel to MN. So we've reduced the problem to showing that AD is parallel to MN. So we can go ahead and get rid of a lot of stuff in the diagram. So let me go ahead and clean it up real quick. So now I've cleaned up things in this diagram. So all the points are the same as before. And now we want to prove that AD is parallel to MN. So how can we go about proving this? Well, it doesn't seem like angle chasing would work. And nor would it seem like homothency would work or any of these advanced techniques. So we might resort to length chasing, like getting a bunch of lengths and then using those to prove the parallel lines. And after looking a bit, we end up coming across BQ equaling CP. We might conjecture this. So how can we go about proving this conjecture? Well, the best way to relate BQ and CP to the other side lengths of the triangle is to use power of a point. Specifically, we know that BQ times BA is equal to BD times BM. So that means that BQ is equal to BD times BM over BA. And similarly, CP is equal to CD times CM over CA. And if we were to prove that these two are equal, then we want to show that these new expressions are equal. So we want to show that they're equal. But now we know that BM equals CM since M is the midpoint. So we can get rid of these. There we go. And now we are just left with proving that BD over BA is equal to CD over CA. But for those who are a bit more experienced, you guys might recognize this as the angle bisector theorem, which states that the ratio of the sides is equal to the ratio of the lengths that get separated by the angle bisector. So AB over AC is equal to BD over DC. And after rearranging a bit of fractions, this implies the result. So now that we know that BQ equals CP, we might want to try doing something with this. And this last part might feel unmotivated, but I'll go ahead and present the solution here. So here it goes. So we set the origin of a vector system to be like anywhere. It can be anywhere, here, here, or here, anywhere. And we let B be the vector corresponding to B, C be the vector corresponding to C, and so on with lowercase letters. Then we know that the length B minus Q is equal to the length C minus P. And the best way to relate this to an angle bisector is by taking a look at this. This vector here has the same magnitude as this vector here. So if we end up shifting things, so if we end up shifting this vector over here, then this vector over here, they still have the same magnitude. But now we know that the sum of these vectors, these two vectors, since they have equal magnitude, have opposite components perpendicular to AD. So the sum of the vectors BQ and CP is parallel to AD. And hence so B minus Q plus C minus P is parallel to AD. So, and if we rearrange this, we have B plus C minus P minus Q is parallel to AD. But now if we divide both sides by 2, we get B plus C over 2 minus P plus Q over 2, which is just equal to M minus N is parallel to AD. But M minus N is just the vector corresponding to Mn, and we are done. And most of you will be like, whoa, where did this argument come from in the first place? Like, what would be the motivation behind this motivation behind this approach? Like, why would one consider vectors in the first place? And I guess the answer is that you have these equal lengths here, and you want to relate the midpoint of two of these to this line AD. And you want to somehow use the midpoints. And you can end up using these vectors, and you end up getting really nice stuff. And if you want to see another technique of how this is used and a better explanation for the motivation behind it, I highly suggest you check out my friend's video linked in the description. So, and one final thing I want to note that appears in this diagram, it appears that these two circles and these two lines concur at the same point X. And go ahead and let me know your proofs in the comments. If you have a proof for that X lies on all of these circles and these two lines, then let me know in the comments. So thank you so much for watching this video. I hope you enjoyed. Please get me to 125 subscribers before the AMC 10A on November 8th.